This video is a review of the history of the atom and the scientists and their theories and how they developed that led us to our current understanding of how an atom works. So the first kind of things you should know before this lesson is you should be able to draw the particle arrangement of solids, liquids and gases. You should have done this before. Now, just to make a point, this diagram in the middle, this diagram about how people typically draw a liquid, is wrong, and the reason is because the particles aren't touching. In a liquid, there shouldn't be any space between the particles. They're just not neatly arranged. So in a solid, you can see these particles are arranged very neatly in rows, whereas in a liquid, they can move freely around each other. So they should be touching each other still all throughout this liquid. They're just not in a specific structured way, and then the particles in a gas are spread out. And you should know how to draw the diagram of an atom. So you should remember that in an atom you have the nucleus in the center, protons and neutrons. Protons have a positive charge, neutrons have a neutral charge, and then electrons around the outside in the shells, which have a -1 charge. You should recall that information. So what you're expected to know is how and why the atomic model has changed over time, be able to describe an atom correctly, recognize the size of an atom as 10 to the -10, and also recognize the names of the scientists and what their contribution was. So objectives wise, you need to be able to explain the key features of an atom, explain the forces inside an atom, and then explain the development of the atom over time and how the different models varied. So this is the first part of P1. So this idea of what the universe is made of is an old question, and we've been developing it for a long time. In Switzerland there is the Hadron Collider, which is the world's largest particle accelerator and world's largest single experiment. It's so big that it crosses over the border between France and Geneva, because it's 27 kilometers all the way around. And what they do at the Hadron Collider is they smash together inside the particle accelerator the parts of atoms, and the reason they do that is to try and smash it into little pieces to work out what it's made out of. And from this we've discovered lots of new particles. So the whole purpose of this lesson is for you to understand, well, if we're still doing this, if we're still exploring what an atom is like, what did we used to think it was like, and why have we changed our understanding over time? So there's lots that you should remember about protons, neutrons and electrons. Now the first thing that you should know is that protons and neutrons are both in the nucleus and electrons are in the shells. Protons are positively charged with a +1 charge, and neutrons are neutral, they have a 0 charge. Electrons have a -1 charge, so they are negative. So protons are positive and electrons are negative. Remember, neutron, the neutral bit, that is for the 0 charge. Now, the mass of protons and neutrons is the same. They both have a mass of 1, whereas electrons are 2,000 times smaller than protons and neutrons. So remember, if you're unsure about the relative mass, it's always 1 for the mass for protons and neutrons. Now, this information here at the top is all the basic information you should recall from Introduction to Chemistry, so you should know this already. The next bit is sort of to build your knowledge. So protons, on the periodic table, the way we know how a proton works is, how many protons there are rather, is if I look at the periodic table for like lithium, I would see that it's 7 and 3. Now the number at the bottom, that is the atomic number or the proton number. That tells me how many protons there are. So in lithium there are 3 protons. The neutron number is the mass number, which is the number at the top here, the 7. Take away the atomic number, so 7 take away 3. That means that in lithium there are 4 neutrons. Now if it's an atom, then the number of protons and electrons is always the same. So if I've got 3 protons, I have to have 3 electrons. If it's an ion, which is a charged particle, so if it's +1, it's +1 because it's got 3 protons, 3 positives, but it's lost one of its electrons, so it's only got 2 electrons now. So instead of this number being the same, it's lost an electron, which is why overall it's positive. If it had gained some electrons, so for example, fluorine, which would look 19, and that would be -1. So fluorine would be 9 protons minus 1. So instead of being 9 electrons, it'd be 10 electrons, and then 19 minus 9 is 10 neutrons. So there's a different example. So atoms always have the same number of protons and electrons. Neutrons can vary though. Neutrons, if you've got different numbers of those, are called isotopes. So protons were discovered by Ernst Rutherford, as we will discuss in a moment. Neutrons were discovered last. They were discovered by James Chadwick, and the reason it was difficult for those to be discovered was because they don't have an electrical charge. Because the charge is 0, it's very difficult to detect them. And electrons, they were actually discovered first, and they were discovered by J.J. Thomson in 1897. And he used this to come up with his plum pudding model. So for an element, the number of protons never changes, and the last things we can say about electrons is that they can be gained or lost to form ions, as we've just discussed here, and they are always in shells, so 2 electrons in the first shell and then 8 in every shell after that. So if we think about a nucleus, this nucleus here couldn't happen. We can't have a nucleus that's all positively charged, because what would happen is each of these protons, each of these positives, would repel each other, and so that would create an outward force on the nucleus, and so it would explode. It would be unstable. That's the word that we use to describe it, unstable. So if I've got a large nucleus, all of the positively charged protons will repel each other, just like little magnets repelling each other, and that it creates a repulsive electrical force, which is one of the forces inside the nucleus. So the repulsive electrical force is caused by the protons outwards. Now clearly a nucleus doesn't always do this, so there must be an attractive force that holds it together. Now scientists used to think this was gravity, but the mass of the nucleus is so incredibly tiny that gravity is almost non-existent. It is there, but it's so small that we ignore it all the time with nuclear physics. So there has to be another force holding it together, which is why we have neutrons. So they produce an attractive nuclear force to hold it together, and we call this the strong nuclear force. So there are 2 forces inside our nucleus: the strong nuclear force, which is attractive and that holds it together, and the electrostatic or electrical repulsive force that makes it want to decay and become unstable. So when this happens with a small nucleus and the forces are balanced, the nucleus is quite content and doesn't do anything bizarre. So the forces are balanced, and that means that there's no resultant force inside the nucleus, the density remains constant, and most importantly, I know you can't see that, it is stable. Now with a very, very large nucleus, that same thing doesn't happen. There's now a massive repulsive force which has to cause something to happen. So what the nucleus does is it fires out some protons and neutrons to reduce that overall charge, and this is what we call radiation. So radioactive decay is caused when a nucleus is unstable. So it's very important for us to be able to explain how radiation works, that we understand the forces inside the nucleus. So now we move on to the scientists and their contributions to the development of the atom. So first we have Democritus and John Dalton, whose contribution was to consider atoms as uncuttable particles, or as Democritus originally called them, atmos. Now Democritus was ignored when he originally suggested this idea, but John Dalton brought the idea back more than 2,000 years later. Then J.J. Thomson developed John Dalton's original ideas and discovered the electron. And he then realised that an atom wasn't simply a hard sphere of an uncuttable particle, but it had components, and one of them was a negative electron. So he developed the plum pudding model. Then we have Ernst Rutherford, who developed, using his gold leaf experiment, the nuclear model of the atom, and he did this in 1911. And then finally there's Niels Bohr, who built Rutherford's model further by saying that electrons didn't just orbit a nucleus, but they also orbited in shells. So, seeing these models, Democritus and John Dalton thought of an atom just as a single sphere. J.J. Thomson discovered the electron, so his plum pudding model consisted of these negatively charged plums. Those are negative particles, those are his electrons, in a cloud of positive. So all this blue sphere he considered just to be a positive cloud. Now, Rutherford, through his gold leaf experiment, suggested that this wasn't the case, and that the nucleus had to be in the centre of the atom with all the mass there, and that that's where the positive charge is located, and that the electrons orbit around the outside. Niels Bohr then added the shell model by saying that the electrons didn't just orbit randomly, that they had to be in specific energy levels. This has then been developed further, and scientists develop new theories further when there is evidence, so they need evidence to change their theories. So we call this the plum pudding, the atomic model, and then electron shells. So looking at these experiments in a little bit more detail, the one experiment you need to know the most about is Rutherford's gold foil or gold leaf experiment. Now what he did in this experiment is he had a source of alpha particles. Now alpha particles are a type of radiation, and this is what is emitted from an unstable nucleus. So he had some alpha particles and he fired them at a gold leaf, which is basically just a really thin piece of gold that's been hammered so that it's only a few atoms thick. And what he did was he observed using a detector where these alpha particles went. So he had several observations. Now the first was that most of the alpha particles passed straight through. So if you imagine an atom as Rutherford eventually imagined it, with his nucleus and his in the centre and his electrons around the outside, the ones that passed straight through passed not next to the nucleus, they just went straight through because most of the atom is empty space. The second observation was that some were slightly deflected, so some particles went very close to the nucleus and therefore were slightly deflected, and that's because the nucleus, remember, is positive, and an alpha particle, which is made up of a helium nucleus, so it's got 2 protons, it's also got 2 neutrons, and it's got a +2 charge because it's 2 protons, which each one's +1. So an alpha particle is also positive, and so they repel each other. So this means the nucleus must be positive. And occasionally some of them bounced back, like this one here. Now this was really unexpected by Rutherford, and what this suggested was that some of the particles had to have collided with all the central mass, which must be in the centre, and then been deflected by greater than 90 degrees. So these were his 3 observations, that most passed straight through, some were slightly deflected, and some were deflected by angles greater than 90 degrees. His interpretations for each of these is that, well, if most of them pass through, most of the atom must be empty space. If some of them are slightly deflected, it means the nucleus must be positive, as the alpha particle is. And lastly, because some of them are deflected back by a large amount, most of the nucleus's mass must be in the centre, which is what he called a nucleus. So you need to understand this experiment and the models proposed by our 5 scientists, so Democritus and Dalton, J.J. Thomson, Ernst Rutherford and Niels Bohr. And remember that Dalton and Democritus believed in an uncuttable atom, which is just a hard sphere. Thomson came with the plum pudding model with his negatively charged plums and positive cloud. Rutherford came to the atomic model with the nucleus in the centre and the electrons around the outside. And then lastly, Bohr added the idea of electron shells. You should be able to explain this confidently.